Alright, so this is the sixth video in the series of name reactions, and today we are going to discuss about Appel reaction. So here's a question for you. I want you to find out the reagent required to convert this particular alcohol where OH is above the plane into the following product where chlorine is below the plane in a single step. The second question for you is I want to convert my amide functional group into a nitrile functional group in a single step. So this is what we call the Appel reaction. So now let's go ahead and discuss Appel reaction, their reaction mechanism, and some practice problems as well. Okay, so we have this particular alcohol where OH is above the plane, and I want to convert it into a haloalkane where chlorine is below the plane. So this is what we call the Appel reaction, where stereochemistry is getting reversed and you are converting alcohol into haloalkane. So the reagent you need is, you need a triphenyl phosphine with carbon tetrachloride, or you can use carbon tetrabromide. So this is all you need to convert your alcohol into haloalkane and reverse the stereochemistry. So let's see the mechanism. So we have PPS3 and this phosphorus has one lone pair of electron. Let's start with CCl4 because we want Cl in our product. So this is the structure of carbon tetrachloride. Okay, so this phosphorus will attack at this chlorine with its lone pair, and this single bond with its bond pair will collapse on carbon. So this will give me PH3P now bonded with chlorine. Now this phosphorus has 4 bonds, so it will get positive charge, and here we have CCl3 with a negative charge. So this is the first step. Now in second step, the alcohol will come and this anion can now act as a base, can take this proton of alcohol and will generate the alkoxy anion. So we have a alkoxy anion. Now this phosphorus has a vacant orbital and a positive charge. So this oxygen with its lone pair will form a bond with this phosphorus and this chloride ion is going to leave. So we will generate oxygen bonded to PPH3. Phosphorus is again forming 4 bonds, so we'll get positive charge. Now we have just removed the chloride anion that will come back. So here this whole group is present above the plane. So this chloride ion will attack from below the plane. This bond will break and will form double bond here. So this is how the stereochemistry is getting reversed, because chlorine is attacking below the plane because OH is present above the plane. So now we have product that is Cl below the plane, and the byproduct is triphenyl phosphine oxide. So this is the mechanism of Appel reaction, where you convert your alcohol into haloalkane using PPS3 and carbon tetrachloride, and you also reverse the stereochemistry. So now let's go ahead and discuss some important practice problems. Okay, so here's a question. We have OH below the plane this time, and we have a OTMS group here, and I'm reacting this with CBr4 carbon tetrabromide and triphenyl phosphine. So pause the video, draw the product and the reaction mechanism. So let's begin. So we can quickly draw the product. All we have to do is replace this OH group with a bromine group this time, because we have used carbon tetrabromide, and we have to change the stereochemistry. So the product will look like, so OH is below the plane, so I will keep my bromide above the plane and rest will be same. So this is the product for this particular reaction. Let's quickly draw the mechanism for this one. So I have triphenylphosphine. Phosphorus has this lone pair of electrons. We have carbon tetrabromide. So this phosphorus will form a bond with bromine. This bond will collapse on carbon. So this will give me this particular intermediate along with CBr3 minus, which will now act as a base. So this will now act as a base, will take the proton of alcohol, will generate a alkoxy anion, and this will give me oxygen bearing negative charge, and rest will be same. Now at this point of time, this oxygen will form bond with phosphorus. This bromide ion is going to leave. So we have oxygen bonded with PPH3, phosphorus having 4 bonds will get positive charge, and rest is same. And at the last step, we have just removed bromide anion that will come back. Okay, so bromide ion will come back. So this group is present below the plane, so it will attack above the plane. And this bond will form double bond here, and this is how you get the product. So we changed the stereochemistry from below the plane to above the plane and converted OH into Br, and rest will be same. So this is the product and the mechanism for this particular reaction. Okay, here's another question for you. So we have this time PHCH2OH, and I'm reacting this with PPH3, and we have 1,2-diiodoethane. So CH2CH2I. So this is my another reagent, a source of iodide ion, and the product will be this one. So simply we converted OH into iodine. So try the mechanism. Let's go ahead and write the mechanism for this one. So mechanism will be same, the idea is same. So this phosphorus with its lone pair will grab this iodine, will generate carb anion here. Phosphorus is now bonded with iodine. Phosphorus will get positive charge, and we have a base now, a carbon ion which will act as a base now. We have an alcohol. This base will grab this proton of alcohol, will generate alkoxy anion, and we have O minus. Now this O minus will form bond with phosphorus. Iodide ion is going to leave. This will give me PHCH2O bonded with PPH3. Right? So this iodide ion will come back, will attack at this center. This single bond will migrate here, will form double bond, and the product is PH. So we connected this CH2 with iodine. We got the product and the byproduct, that is triphenylphosphine oxide. So this is another way of substituting your OH with the iodine by using this particular reagent, that is 1,2-diiodoethane in presence of triphenylphosphine. Okay, here's another question. This is very interesting question. So the starting material is, we have this time a epoxide present above the plane, and we are reacting it with oxalyl chloride and we also reacting this with PH3 P double bond O. So the structure of oxalyl chloride is COCl twice. So this CO represents carbonyl group. So we have a dimer of this COCl. So this is my carbonyl, this is my Cl, and we have a dimer of it. So this is the structure of oxalyl chloride. So pause the video and react your epoxide, which is present above the plane, with this particular PPH3PO with this oxalyl chloride, and find out the product with mechanism and specified stereochemistry. So let's go ahead. So we have oxalyl chloride, and we have this triphenyl bonded to phosphorus, right? So now what happens is this oxygen with its double bond will attack at this carbonyl, and through conjugation Cl is going to leave, right? So we have Cl, C double bond O, C double bond O intact. This is now bonded with oxygen, which is bonded with PPH3. Okay, so this double bond used one of its bond to attack at this carbonyl, and through conjugation with this oxygen Cl is going to leave, and you generate this intermediate. Now we have just removed the chloride anion. Here phosphorus having one positive charge. So we just removed this chloride ion. Now this will come, will form a bond with this phosphorus. Okay, this bond will migrate here, this bond will migrate here, and this bond is going to break. So let's draw the possible products we are getting out of here. So this Cl is getting bonded with phosphorus, so we have PH3P bonded with Cl, phosphorus getting positive charge. We are forming a CO2 here, right? So we are eliminating CO2 as a gas. We are forming CO, that is nothing but carbon monoxide, that also eliminate as a gas, and we are also eliminating the chloride ion. So we formed all this. Okay, so just to recall, this molecule with its double bond attack at this carbonyl, Cl is going to leave, you generate this. So whatever Cl just left will attack here, this bond migrates here, this here, and Cl going to leave, and you form this sets of product. Now let's go ahead and write the next step. Okay, so we have formed PH3P bonded with Cl. We have formed CO2, which leave out as a gas, CO, which leave out as a gas, and we have chloride ion. So we have formed this much in our first step. Now we have a epoxide present above the plane, right? So this chloride ion will attack at this carbon, the less hindered site it will attack, and this bond is going to open. So epoxide is present above the plane, so chloride will attack from below the plane, and you get R. So OH, so this becomes O minus now, which is above the plane, and Cl is present below the plane. So this Cl opens up this epoxide ring, forms O minus, which is above the plane, and Cl attacking from below the plane. So now we have this particular intermediate, and we have also formed this one. So this will come into picture now. So this oxygen will form bond with phosphorus, Cl is going to leave. So you generate oxygen bonded with PPH3 plus When phosphorus have 4 bonds, it will get 1 positive charge. And we have Cl here, below the plane. Now we again removed a chloride ion, that will come back. And this group is above the plane, so it will attack from below the plane. This will form a double bond here. Similar mechanism like previous one, and you get the product. So Cl is below the plane. This Cl is attacking from below the plane because this whole group is present above the plane. So you get Cl below the plane. And this is the product for your reaction where both the chloride ion are present below the plane starting from epoxide, which is above the plane. So this is the product for this reaction, and this is the reaction mechanism. Okay, so here's another question. So let's discuss our amide conversion into nitrile. So remember the question was, we have this amide and I want to convert this into a nitrile in a single step. So you can use Appel reaction. You can add oxalyl chloride with triphenyl phosphine oxide. Okay. Make sure you try the reaction mechanism. So let's do it. So we have oxalyl chloride. Okay. And we have this triphenyl phosphine oxide. So this double bond will be used up to attack at this carbonyl. And through conjugation, Cl is going to leave and you generate Cl, C double bond O, C double bond O, oxygen, PPH3. Now phosphorus will get positive charge. Now, so we removed Cl minus, that will come back, will form bond with this phosphorus. This will form CO2, this will form carbon monoxide, and another Cl minus is going to leave. The same mechanism like previous one. So we have generated PPH3 bonded with Cl, phosphorus getting positive charge. We also have a Cl minus. So for a time being we have this much. Now we have a amide, right? So let me make some space. Okay, so we have generated this reactive intermediate and we have a amide. So this is my amide and we have just generated this particular intermediate. So this oxygen with its lone pair will form bond with phosphorus, will eliminate chloride anion, and this will give me R, C double bond O bonded with PPH3, this oxygen getting positive charge, and you have NH2. So we have 2 chloride ion now, 1 and we just removed 2. So one of them will come, will take this proton, this will form double bond here and this oxygen will get neutralized, correct? And you get R singly bonded with OPPH3. This phosphorus will also get positive charge, okay? And you have a double bond here with NH. Okay, so we used one of the Cl, let's use the another Cl present. So this Cl will grab this proton. Now this single bond will be used to form a triple bond and this bond will form double bond here. So the product is RC triply bonded with N and the byproduct is triphenyl phosphine oxide and we got the product RCN. So this is very interesting for your exams where you might be asked to convert your amide into a nitrile in a single step, then you need to think about all this. Doing Appel reaction using oxalyl chloride and triphenyl phosphine oxide, and this is the reaction mechanism for it. Okay, so here's the another question. This time we have a alkyne group. Okay, this represents a carbon. So this is a carbon and this is a carbon, because alkyne is a linear molecule. We have OH present above the plane and we have a aryl group. Okay, now I'm reacting this with CCl4 and PPH3. So what is the product? Find out the product and the reaction mechanism for this particular reaction. So let's begin. So we have a triphenyl phosphine. We have CCl4. Well, this is an Appel reaction. So this phosphorus will take this chloride and this bond will fall on carbon and we get this one. And the byproduct is CCl3 minus, which will now act as a base and will take the proton from the OH and will generate alkoxy ion. So we get oxygen bearing negative charge and Ar group. Now this oxygen with its lone pair will form bond with phosphorus. This Cl is going to leave and you generate R alkyne oxygen bonded with PPH3. This phosphorus getting positive charge and here we have a Ar group. Now at this point of time we have just removed Cl minus, that can come back. So now what do you think? Where this Cl is going to attack? So ideally it should attack at this carbon and should form Cl bond here below the plane, because this O is present above the plane. But instead this chloride ion will attack at this alkyne carbon. This triple bond, one of the bond will form double bond here, and this bond is going to break to form the triphenyl phosphine oxide. So why does it happen? Simply because this triple bond in it's such a way that it can do arrow push type of mechanism and can eliminate this triphenyl phosphine oxide. This alkyne is sort of acting like a neck-bearing group participating, and this is how this Cl attacks here, this triple bond migrates here, a sort of arrow pushing mechanism. That's why this Cl prefers to attack at this alkyne center. And we get, so this time we are getting, so this is my CH2, we have a double bond, another double bond, and we have a Ar. Correct? Let's number them. So this is 1, 2, 3, 4, and this 5 is Ar. So this is my 1, 2, 3, 4, and 5. Okay? And Cl is present at the 2 position. So let's keep Cl here. Correct? So this is the product for this reaction, where you convert alkyne into a alene, and you also remove this OH group. So this was a interesting question. So that's it for today. This was the 6th video in the series of name reactions. We'll be solving more and more, we'll be understanding more and more name reactions in organic chemistry in future videos. So thank you for watching. Goodbye.